So I'm going to transition us into the marine environment and tell you about some work that we've been doing at Lamont to make elevation data accessible to non-specialist users. So I think it's pretty clear from what we're all working on that topography is a fundamental earth science data set. And really the surface, extends deep into the ocean, which covers the majority of the planet. I was first putting this list of uses of topography data together, thinking only about the ocean, but really it transcends both environments. There might be a few more specific things for ocean research and exploration because we know so little about the ocean, which affects how we plan our field programs. Also, the ocean's very inaccessible. We can't go there and visit it repeatedly and look at it with our eyes. And when we do go there, we're looking sort of through a straw at a very limited view. It's very expensive to get there, et cetera. And also when there's things like ocean search and rescue efforts, like the MH370 plane crash, we don't really have very good base maps to start from to plan those kinds of reconnaissance missions to find wreckage. And we can't deploy robotic vehicles without having those sort of fundamental base maps. So I tried to step back a little and think about the different modes of accessing elevation data and thinking about the continuum between non-specialist and specialist users. And sort of at one end of the spectrum, from the non-specialist perspective, you might have a phone app where you're looking at a map. You might want to interrogate that for a z-value. You might also want to interrogate some surface that's been rendered for you and maybe make profiles if you don't have the skill set to do that and grid the data yourself. That's sort of the least specialized access. You also might want to interrogate a data set and extract a raster at some custom resolution for some area of interest. You might also want to go and find the source data, whether it be the raw data or the point clouds or individual grids, and do various analyses with those. And then even further along the specialist spectrum, perhaps, is programmatic access, computer to computer, querying services to get values or grids or images through web services. Likewise, there's variable format requirements from the non-specialist to specialist spectrum or continuum, from images to grids and point clouds, and then all the way back to the source data. So trying to make sure that these different formats are available, I think, is a very important task. And then, of course, there's variable resolution requirements that are driven presumably by the science questions that you're trying to answer. So what you're seeing there is a roughly 1 kilometer bathymetric map derived from satellite altimetry data and it's predicted bathymetry. That kind of scale might be perfectly fine for large-scale ocean circulation work or global kind of geophysical questions. If we zoom in a little to 100-meter or even down to like 5-meter resolution, you get a lot more detail. That would be appropriate for different kinds of questions. And you might have to go all the way into sub-meter resolution. This map is a hydrothermal vent field in over 2 kilometers of water depth that I mapped with a remote operated vehicle. And you can actually see individual vent structures. So it really depends on the questions you're trying to ask or answer. So then we get to the problem that water conceals the vast majority of our planet, and the majority of what we've got for global ocean maps are predicted. So this is a really simple way of showing sort of the whole scale of the planet, roughly 70% of that being ocean. And then our best estimates are maybe less than 15% of that has actually been mapped with direct measurement. And of those measurements, not all of them are modern methods. Some of them might be lead line, literally dropping the weight off the side of the ship. Some of those might be contours. So we really don't have a lot of information. And again, as I said, we don't know what it's like to be there. So this is a visualization where I was, this is actually a point cloud rendition of a grid. I realize that that's a little bit weird, but it was an experiment, and we used it in a VR cave to see, what would it be like if we're standing on the seafloor? We really have no idea what that's like because we can't do it. So when we think about bathymetry data globally, it's very sparse. We have very little redundancy. The map on the left, the little track line of higher resolution there is an older multi-beam sonar system, with a very narrow swath width, and less resolution. The track on the right side is a more modern one, so we're getting more coverage and better resolution. But all of this information is really important if we're going to splice together a global ocean map. We also have the apples to oranges problem that we can't get away from because the data are so sparse and so rare. We have to really pull all of it together. So there's different platforms being used, different sensors being used. The little shot on the bottom right there is an experiment that I did making a 5-centimeter resolution grid from another vent field. It's really pushing the limitations of the sensor, and also the underwater navigation is a huge limitation for it. So if we step back to the more ship-based data, what is publicly available at the NOAA archive is primarily raw ship-based data. That little network of track lines that you see on the right side might look like there's quite a bit of data density, but of course that's a scaling issue. And when you zoom in, you'll see that the distance between those lines is massive. And of that data that's publicly available, and it's largely publicly available because there's been a lot of focus at NSF to make sure that the data that we collect is made available. Of that data, it's pretty much all raw, and we need to have specialist knowledge to be able to distill that from the raw sonar format into something that's usable. The bottom left plot there just shows the increase in multi-beam data, expeditions that have acquired multi-beam sonar data over the years from 1980 to present. So we're collecting a lot of data now. It's becoming available, but there's a lot of work to do to integrate it. And how do we do that? Preparation and integration. Well, there's a lot of, I think, unique challenges that we have in the submarine environment, and probably a lot of similarities. I'm not super well versed with LiDAR and other optical imaging techniques, but we have things like, bad navigation, sensor problems. We also can have, so most of these systems are hull mounted, and we can have biofouling on those systems, which obscures the signal and makes it harder for us to work with the data. We might have dropouts from bad weather. We don't have the options to go back and resurvey sometimes. We're on our way someplace trying to make use of all this data. And so these shots on the right are just some examples of some of the problems that we try to address as we process the data. So this brings me to the global multi-resolution topography synthesis, which we've been curating at Lamont since the early 90s. It started first focused on mid-ocean ridges and has expanded to the global ocean and also includes terrestrial data. The goal of this project is to make a data compilation that's freely available and helps to deliver the best possible elevation data for a diverse user community, recognizing that we all want to push the data to the best resolution. We're sort of the specialized community here that really wants to go maybe a little bit deeper, but trying to find a sweet spot of what we can do to provide broad access for the community. So we're combining sparse multi-resolutional data to make more complete grids and maps. We're trying to enable access across disciplines, from biologists who might be less well-versed with how to work with sonar data but need it for their work, to chemists, to geophysicists. We really want to make sure that we're meeting the needs across that continuum and that we offer different access pathways and formats so that everyone can make use of the data. So a lot of our effort has been focused on processing and integrating this publicly available data from NOAA. One of the objectives there, of course, is to improve science efficiency, mitigating the need for everyone to go and process their own data. So we're going to help make it faster and easier for people to access the data. But we're also providing links back to that SWOS data, so the source files, in the processed form. The raw ones are at NOAA and can also be accessed for people who need that. We also focus on consuming and integrating publicly available gridded data products. And in that case, we take them sort of as is. We might try to deal with the datum shift, but we then just provide links back to the source grids if people need access to that. So the way that I like to describe GMRP is that it has basically 4 discrete components that we maintain independently on the back end, and we update them at different schedules. So the topography data, which is relatively static because we're mostly marine geophysicists, is a combination of the ASTER data and the NED data set. So I don't think we've updated that in quite a few years. It's a pretty large data set by our global perspective. So we're happy to sort of leave that until we need to update it. We use the GEBCO compilation, which is an international compilation of bathymetric data, which is roughly a kilometer resolution. So that is largely, again, sourced by this predicted bathymetry and then constrained in some places by actual observation. We then take contributed grids of variable resolution from less than 1 meter, like those hydrothermal vent maps I showed you, to hundreds of meters in grid size. And then the swath bathymetry that we curate is always gridded at least at 100-meter resolution, sometimes better if the data can support it. And so we basically take these components and we put them together at various resolutions and pre-compose images. But if the user needs to come in and request a grid, they set their bounding box and they set their resolution request. And we compose these components on the fly to deliver to them the best possible gridded data set. So this is just a little workflow diagram to show how we manage the bathymetry data. We sometimes make use of commercial processing software, but ultimately we push it through open source software called NB Systems to generate these processed files. We then grid that into grids based on individual cruises. And that is what gets pushed into the GMRP compilation. Those processed data files go into basically a file database repository that sits behind a metadata catalog so people can come and search for and download those files directly. So just some numbers on where we're at with this. Again, this compilation has been going on since the early 90s. Just from the swath data that we curate, we have an estimated 8.3% of the ocean covered, so a really small amount of the ocean covered. That's from over 200,000 swath data files, 200 million pings, over 31 billion points. I won't read you all the numbers, but this is from over 1,000 cruises. We try to add about 2 million square kilometers of data a year. I think, there's quite a bit of backlog still to get through. So we're trying to go as quickly as we can to get the most data in as quickly as possible and get the most bang for our buck. So try to go for the more modern systems with a bigger swath width better. Again, we have this extensive file and cruise level metadata that we maintain in a Postgres database. And I think one of the most important things about how we're doing this is that we're maintaining these input files in the native swath format, so the sonar format. So if in the future we need to go back and reprocess, we can still do that. We can make sound velocity corrections. We can deal with any of the issues that might affect the product. I think a lot of people, when they're dealing with larger scale bathymetry compilations, kind of step away from that, but that provenance and connectivity, I think, is a really critical aspect of what we're doing. So in terms of challenges and opportunities, blending between data sets is, of course, a bit of a challenge. I think back in a few slides ago, I may have said seamlessly delivered the data. And I put it in quotes for this community because you will see that there are themes if you go and look closely. We try to do the best that we can to deal with vertical datums. In the deep sea, there really aren't any, particularly if we use autonomous vehicles. So we often have to shift things to match the ship-based data because what else can we do? We also don't have a very good solution for the coastline, which of course is a really important thing to do. But our focus has really been trying to get the symmetry data put together. We're not doing uncertainty estimates. We could be because of how we have the system architected. We just have to develop a method for doing that, I'd say. We're getting increasing data resolution, faster ping rates, more beams. So that's slowing down processing and integration to some degree. And also it's more data that we have to store. So that's an ongoing challenge. Always trying to develop new processing tools and workflows that really optimize data quality and efficiency. We talked a little bit in one of our groups this morning about versioning and archiving. So if you start from a raw data and make a process version of it, somebody else makes a process version, how many versions do we have to keep? Are there ways to do this more efficiently so that we have the raw files and then the ancillary information perhaps that's necessary to make the process files to get to the products that we're building. Scalability of architecture and formats, of course, is an issue. We're still using our own homegrown grid format that was developed in, I think, the 90s. which works just fine, but it's not GDAL compliant. A lot of our life would be easier in terms of interoperability if we just had a GDAL compliant format, but that would require a rewrite of our whole system. And of course, making things as performant as possible is a big challenge. We've moved all of our data and infrastructure to the Amazon cloud, so we have gained some efficiencies there, but I'm sure we can do more to make it more responsive for users. So some things on the horizon as I think about the Symmetry data. Can we do distributed processing, maybe in the cloud? Can we have better ways of managing elevation data, perhaps not just the Symmetry, so that we have processed, clean data there with provenance information, we know how it was created, and then we can grid it on the fly. Maybe I want data from a couple of different cruises from different times if they go over the same area, or I want to use a different gridding algorithm. Right? We're pretty close to being able to do that if we invest in the CI necessary to do it. Immersive visualization is a really exciting thing, which I mentioned earlier. There's a screenshot here. I love the gentleman who's taking a picture through his phone, not recognizing that his 3D glasses are not in front of his phone. But there's a lot that we don't yet understand about what we might be able to perceive differently about the data in these kinds of environments. So I think there's a lot of exciting potential there. And then in the ocean sciences side of things, there's a lot of new data sources that are coming. So there's an XPRIZE competition right now focused on rapid acquisition of high resolution data with autonomous platforms, including autonomous processing of it. There's crowdsourced Symmetry data initiatives to try to get echo sounders on not just research vessels and big ocean liners, but even small recreational boats. And how do we get that into the mix? And Seabed 2030 is a big international initiative that I'm a part of that's trying to push this. And the general goal of Seabed 2030 is to have a complete ocean map by the year 2030. So recognizing how little of the ocean is mapped is a really grand challenge. And we are engaging with various stakeholders around the world, industry. There's a lot of surveying companies that have mapped a lot of the ocean. We're trying to work with them to see if they can negotiate with their clients to share the data, these kinds of things. But of course, as that happens, we're going to have even more data to have to work with and manage. So just some thoughts to conclude with. I think my general argument is that the access pathways and formats really need to meet the broad interdisciplinary user base and also be able to support the expert access, the needs of the experts, and also make sure that the data are ready for whatever future applications and processing and visualization things are coming. We want to make sure that we're not, going to a dead end and limiting what might be possible in the future. And then just a few questions maybe to inspire conversation. How are we going to best manage and store all the source data as these data volumes grow? In some ways, I was just thinking, as we're listening to the terrestrial data volumes, like my world's a little bit easier because we don't have the kinds of resolution, but we still have the same sorts of challenges to confront. And so what can we leverage across our communities? We think about a lot of the same kinds of problems, so I think that we can gain efficiencies from things that we're doing in the two sides of the air-water interface. And then again, how do we ensure that the products and the archives that we are building are going to be ready for these future opportunities? And that's it, thanks.
All right, questions for Vicki?
You'd think I practiced, but I didn't.
I was just noticing one of the cool things also about the GMRP is its availability to web services and so these multiple pathways. So, I know, for example, I was just looking in OpenTopo, we do a RESTful web service call, and there have been 10,000 downloads, 10,000 jobs GMRP through OT, but there must be many, many more from the main portal as well as the GeoMap app. So, can you kind of comment a little bit more on how it's being used and?
Yeah, so we've done some work looking at access statistics. We haven't really quantified access through GeoMap app. So I didn't explicitly state it, but GMRT is the base map and GeoMap app, if you've heard of GeoMap app. It has a couple of thousand unique users a month. So they're accessing it in some ways. We've just put some hooks in to be able to quantify some information about where they're searching and what they're loading. We know about our web map services and that those are being used pretty broadly globally, different interfaces. And we are trying to, on our webpage, we have some plots that show the count of requests that are coming into the grid service and the image service and the profile service as well.
There's a ESOP data set, or ESOP 5, ESOP 2, ESOP 1. So how is your data compared to that one?
So you're speaking about terrestrial data, I presume, right? Yeah. Yeah, I don't know that I can answer that because my brain is always underwater. I know that the ASTER data and the NED data that we have in there was formatted into GMRP, I think, about 10 years ago or 9 years ago. So that's sort of the state of where it's at. We have 10-meter resolution for parts of the US with the NED data set and 30-meter resolution for other parts of the world. I don't have any comment on or knowledge of, you know, how good that data is vertically or how it compares with other data sets, because I live underwater.
Hi, I asked this earlier in the session. I'm just curious for more clarification. So you're really calling for direct measurement. Well, I guess multi-beam not being considered directly. Something where it's
that's direct in our world.
As direct as possible. And I asked you before about proxy measurements, for example, satellite-based, gravity-based proxies. Is there a hope that in order to create this map that improved or more accurate proxy-based measures will allow you to have that global coverage without needing local sort of in situ measurements? Is there a hope at all?
Yeah, I think so. And certainly, you know, in the coastal environment, I think that there's hope for using other techniques, you know, whether it be bathymetric LiDAR or some other sort of satellite data to help bridge the gap from the coastline into the water. I think that most of our current thinking, at least in the community that I am most closely involved with, is focused on autonomous vehicles that can go and collect large amounts of data with not a huge amount of human intervention. So whether that be facilitated by the X Prize competition or just other things that are evolving. And part of the X Prize competition is that the autonomous vehicle that does the mapping, the bathymetric mapping, has to be deployed from the beach without any human intervention. So it just goes from the beach, it goes offshore, it deploys its thing, does the mapping, it comes back, the data gets processed, and the product is delivered. That's kind of the challenge. And so there's a lot of hope for that kind of thing, and I think also crowdsourcing, which is not going to be super efficient in terms of coverage, but if we can get all the ships, all the boats and ships in the world equipped and feeding in, that's a big data problem to solve, but that can help as well. And I think, you know, as more bathymetric data, which are implicitly remote, yes, as more of those data become available, we can improve the models that are used to do the predictive bathymetry.